before I forget. Yeah, so again, we'll just scratch the surface by this. Yeah. So I guess let's jump right into, and basically, like, if you haven't read, I have the Cracking Coding interview book here, right? And what I'm gonna talk to you about is basically everything that's here for dynamic programming, and highly recommended to read it. And we'll see the implementation in JavaScript. This is written in Java, but it's not that hard to translate it to JavaScript. One step is just not being intimidated by being in a different programming language and actually reading it and you start to draw the similarities and how it can be translated. Okay, so let me share. Let me share my screen. Wait, which screen are you guys seeing? You guys seeing the board?
Yeah, the whiteboard.
Yeah.
Okay, cool. Okay. Cool. So also let me pull. Yeah, actually, by the way, I like to do this is let me put my notes here. I'm gonna put you guys up here so I don't look like I'm looking down. You don't see yourselves, but you are here. Cool. Oh, Ben is coming as well. I told him that I wanted to scratch the surface of dynamic programming. So he'll be coming to like basically support us, provide more context, more color, the way that he knows way more, I think, of this stuff than I do. This is still sort of new for me. But yeah, again, I want us to at least have an idea what it is and not be scared about dynamic programming. I shouldn't, I think I was scared for a lot of time of it, but that shouldn't prevent us from at least taking a look at it. Just like in anything, becoming a master, becoming good will only come with practice. It doesn't come super fast. Okay, so what do we know? Let's start with, so dynamic programming is closely related to recursion. What are the things that we know about recursion again? Anyone, just say, what do you know about recursion?
You need an edge case?
That's correct, an edge case. I don't know why this is not working. We need an edge case. Or what do we call those actually?
Base case?
Base case. Mm-hmm. What else?
Isn't it another way of doing loops?
Yeah. They are looping in a way. What else? It has like, I think we talked about 3 ingredients for recursion. Base case, and there's 2 others. What's one very important one? Involves calling a function. Joy?
Calling the function calling itself.
Yeah, function calling itself.
Recurse.
Calling itself. That is, this is recursing. This is sort of like the key. And what is the last sort of step? This one is a bit more blurry, but I have mentioned it a couple of times.
Is it about the call stack?
Not that one, but let's put it here. Involves call stack. The step that I'm looking for is sometimes referred as the inductive step, or I like to call it the means of moving towards the base case. So any recursion problem must have a mechanism, a means to reach the base case at some point. If we don't have a mean to reach the base case at some point, then the recursion will go on forever and we get a stack overflow error. Or the recursion doesn't go forever, you will always overflow the stack. So I'm going to say means to reach the base case at some point. Okay, so that's like a quick intro to recursion. And something that is almost like inseparable, I guess, from recursion is the fact that recursion works by identifying that a problem is built up of sub-problems that we can solve and reuse our functions, basically. So recursion is built up of solutions to sub-problems. What is an example of sub-problems that you might have seen in like programming challenges or data structures? Anything that you could say about maybe sub-problems? Like also like sort of the divide and conquer.
Edge cases?
Edge cases, say more about that.
Like a lot of them are very specific, so you want to kind of get them out of the way.
But those wouldn't be really sub-problems. But can you give me an example where a problem is made out of sub-problems, or a data structure is made out of sub-data structures?
It could be like deleting the middle node in a linked list.
Okay. Say more about that.
Actually, no, it was like a tree where you have to find all the nodes in the tree, and then if you delete, I guess.
So,
yeah.
But yeah, a tree is a good example. A tree is a recursive data structure because if you have a tree, this is a tree, and then could also be a tree, and this also is a tree on its own, right? So this is like sub trees. That's what we will call this. And then that is also, this recursive data structure is very easy to traverse using recursion. Because recursion is all about sub problems and solving those. What's another example? This is an example with a data structure.
Like shortest path in a graph.
Shortest path in a graph. That is, yeah, that is one. That's one. We're not gonna see that one. I think that is a dynamic programming problem. That's a dynamic programming problem, but we're not gonna get to see that one today. But yeah, that's one. What about one we saw like 2 weeks ago? binary search. Right? Binary search, we implemented binary search recursively the other day. And we could do that recursively because binary search is made out of, or we could think of it as made out of subproblems, where we first look at the array, we look at the beginning and the end, calculate a middle, we check if the value that we're looking for is exactly the middle. If it's less than the middle, then we'll search the left. If it's greater than the middle, we'll search the right. And there, then we just do the same stuff again. We have a start, we have an end, calculate the middle, check if that's one, if that's the one that we're looking for, and just repeat, basically. So binary search is an example where the algorithm is the same, we're just calling it on subproblems. If we have an array of 8 elements, the second time we'll call it on an array of 4, and an array of 2, and so on. Cutting the problem in half. Let's see. What's another example? Fibonacci. And let's say, we'll say factorial. These are some examples. This tree is also a subproblem. Merge sort, which can be implemented recursively, it works also on subproblems. On dividing the array in halves and then merging them. Okay, so that is like generally recursion operates on solutions that are made out of subproblems, basically. Does that make any sense? Any thoughts or questions on that? Okay. So now talking a little bit more on dynamic programming, we're going to see a Stack Overflow question posed as well. These are kind of problems that are that you can find have a dynamic programming solution. Design an algorithm to compute the nth whatever number or the nth whatever. Write code to list the first n whatever things. Implement a method to compute all permutations, all variations, how many times can something be done, and so on. These are all problems that should give you a hint that those problems might require dynamic programming. The example we're going to look at today is with Fibonacci recursive algorithm. Give me a thumbs up if you think you will be able to write the Fibonacci recursive algorithm from memory.
What's the Fibonacci again? Sorry.
The Fibonacci sequence is a mathematical sequence. Fibonacci. Fibonacci sequence. This. So this is a sequence of numbers that go like this, and they grow. Each number, let's start from 2. Each number is equal to the sum of the 2 previous numbers. So 2 is equal to 1 plus 1, right? And 3 will be equal to 2 plus 1, that's 3, and so on. Each number in the sequence is made up of the 2 previous numbers. And we have 5. 5 is made up of the 2 previous numbers in the sequel, which is 2 and 3, and so on and so forth to infinity. So give me a thumbs up, and no worries if you don't put the thumbs up, that's also fine. Give me a thumbs up if you feel like you will be able to write the algorithm to calculate the nth Fibonacci number from memory. Okay. Okay, that's fine. That's totally fine. I think this one is a classic. I think this one you should know by memory. The Fibonacci, the write an algorithm that finds the nth Fibonacci number is a classic, or having an algorithm that prints all the Fibonacci sequence. All those are kind of a classic recursion algorithm. I think we talked about it when we introduced you to recursion. I think it was one of the first recursion algorithms that we talked about, and so on. Oh, Ben just joined. Hey, Ben.
Hi.
Okay, so
Small class today.
yeah, I was thinking that, yeah, dynamic programming is intimidating, and
Oh, yeah.
and I'm no expert as well. But again, as I was saying earlier, we just wanted to scratch the surface here. Okay, so the Fibonacci sequence is this sequence of numbers that happen on nature like often, and it's kind of cool because it's very common. A few examples, and I was actually I think I actually was trying to make something here. Let's see. So it was the other day. This is actually a photo I took. This is a purple cabbage, and for some reason I wanted to slice it exactly for the middle. And then when I looked at it, it looks like it has some patterns, and I thought that was kind of cool. So I took a photo of it, and what I did today was I put, where did it go? Yeah, I put the Fibonacci sequence on top of it, and it matches more or less, which is kind of cool. So you will see this sequence that I forgot who derived it. It was some mathematician, and it's all around nature basically.
His name was Fibonacci.
Well, that was his last name, I imagine. Yeah. Thank you for that. That makes sense. And yeah, like this was the other day. I also took this photo out in my garden. There's a shell of a slug, and you can also see it in the galaxy. So it's kind of cool because it's something that you see at a large scale, like a galaxy, but you also see it as a tiny thing like the shell of a slug. And yeah, this is that basically, where we start here in the middle. Let me see if I can make this a bit bigger. We start with one and one, and you could think of it like, a square of 1 by 1, 1 centimeter, 1 inch, doesn't really matter what it is. And you basically draw an arch or an arc. I don't know the right way to pronounce it, but you draw it from one
curve.
side. That is a better word. Yeah, a curve. As you know, maybe actually let's do it like here on the 5. What am I trying to say here? What is the? I should have.
Okay, so basically, it's like Fibonacci sequence is the sum of the previous two numbers. This visualization is really neat because if we can think about a square is a visualization of a number, right? Some number, let's say 10. We can make a 10 by 10 square, right? And we know the edges of the square are 10. So these squares are just visualizations of scalars, right? So we can say 1 is a 1 by 1 square. 2 is a 2 by 2 square. 3 is a 3 by 3 square, right? So that's just like that's the baseline. What we're gonna say is, in order to like visualize the Fibonacci sequence, which is the sequence of the sum of the previous two numbers, we can say, well, the sum of the previous two numbers is the same as the sum of the edges of the previous two squares, because a square is just as tall or as wide as its number, right? So if we have 1 and 1, then the next one is going to be 1 plus 1 is 2. Then we're going to have a box which is 2, which is twice as big as 1. It's going to be the same height as those two boxes stacked, right? So 2 is the same height as 1 and 1 because 1 plus 1 is 2. The box 2, 2 by 2. The only reason why the box 2 by 2 is just a way for us to visualize, right? So we can think about it just like 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 2 is 5, etc. But this visualization is really cool because we can say the sum of the previous two numbers is also just the same as the sum of the like width or height of the previous two boxes, right? And so if we alternate width and height, that's how we get this spiral. We start with 1 and 1 height and we add them together to get 2. And then we add 2 and 1 width to get 3. And then we add 3 and 2 height to get 5. And then we add 5 and 3 width to get 8, right? And so the reason why we do that alternation is so that A, creates this beautiful visual pattern. B, it's packed tightly, right? If we don't do it alternated, it would be like 1 and 1 is 2. Or I can draw on your screen, right? Can I draw on your screen?
Yeah, I think so.
Yeah. Like imagine if you didn't do it, you know, if you did like 1 and 1 is 2, and then you're like, okay, 2 and 1 would be like, this is 1, you know, it'd be like 3 would be like that, right? Which is 2 and 1. You know what I mean? And then we wanted to do like, so this one is 3, right? And then we would be like 3 and 2 is 5. You know, this is just another way to visualize it. It's not as beautiful. So instead of always doing height, this would be height every time. We're going to do height and then width and then height and then width and then height, etc., etc. Does that make sense?
Mm-hmm.
I'm erasing what I drew because it's ugly.
I actually have never like thought about how it's one height, then width, height, then width. I think that makes
Right.
sense.
So 8 is this, like 8 is the sum of the previous two boxes width. In fact, it's the sum of all the previous boxes width together because the boxes always include the previous one, right? If some number X is the sum, this is important for the software that's coming up. If some number X is the sum of the previous number, like let's say X sub n, right? Xn is the sum of Xn minus 1 and Xn minus 2. Then when I go to the next number, Xn plus 1, it's going to include all the numbers before it, right? Like because some number Xn is the sum of the previous two numbers, then the next number is going to be the sum of those previous two numbers plus the new number, right? It's like all of them are always added together because even if you're only adding the past two numbers, you can say, well, that previous number is the sum of its previous numbers, and that previous number is the sum of its previous number. So that's why this image is very tightly packed, is because the width of 5 and 3, well, where did the width of 3 come from? The width of 3 came from the fact that 3 was the sum of the widths of 2 and 1, right? And then the width of 5 came from the fact that the height of 5 is the sum of the heights of 3 and 2 because we alternate. And then the beauty is that 8 will now fit perfectly because 8 will be exactly the sum of 5 and 3, which is the width of our entire thing. And it will be some new height. And you'll see that the height is always, it's growing, right? It's going to grow. It's going to grow up, and then it's going to grow over, then it's going to go down, then it's going to go right, then it's going to go up, then it's going to go over, and then it's going to go down, then it's going to go right. In this visualization.
Thank you for that, man.
Yeah, I don't know.
This is, I think it is kind of cool. I think it's the fact that it's in nature is really interesting, and that, you know, somebody discovered it. Okay, so let's then, I was saying this is sort of a classic algorithm used to study recursion and used to study dynamic programming and memoization. That's what we'll do here today. So let's go back here. Okay, actually, let's go to REPL and something. Let me share this. I'm gonna share it here in the chat. So recursively, we're always given the we know the start of the sequence. The start of the sequence is 0, 1, and 1. And with those two numbers, then we can get to any other number. So we can say f of 0, 0, f of 1, 1, f of 2 is 1. When we talk about the nth Fibonacci number, and I always get a bit tripped off by this, is we'll start counting from 0. As if there was indices in an array. So yeah, so sort of like the second. Actually, let's put the sequence here. 1, 2, 3, 5, 8. 13. Okay. So we will know that f of 3. We know that any Fibonacci number is always the sum of its two previous ones. So we know that f of 3 will be f of 2 plus f of 1. So in this case, will be 2. Does this make sense? We're gonna use, and our recursion will do exactly this. So what will be f of 4? Can somebody complete f of 4 for me, or tell me what to type?
Come on. You want me to call on someone? I'm all
Sure.
about that.
Yeah.
Brianne, you're the only one with your actually no, there's a lot of people with cameras off. You're the only one whose face, I guess also Jonathan Fagan. Brianne or Jonathan, that's one of you got to speak up. Oh, Jonathan's face is in. All right, it's Brianne then. It's got to be Brianne. Brianne, what should we type?
I don't know.
What is the definition of a Fibonacci sequence? How do we define it?
I don't know.
You don't know?
No.
Google it. Google it right now. Brianne, go Google it. Open a new tab, Google Fibonacci sequence, and just read aloud what you're reading, okay? Tell us all what you're reading.
Okay, hold on. Okay, each number equals the sum of the two numbers before.
Stop. Okay, great. So what should we write here on line 5?
F3 plus F2.
Wonderful. Well done, Brianne. That was fast. When in doubt, Google it. Don't be afraid. Don't be afraid to Google it.
Okay, cool.
100%. Okay, thank you for that. So what would this be then? What is the result of this? What's f of 3? We know that that's 2.
Let's go with Sergio. Sergio, what's f of 3?
2,
And what's f of 2?
1,
So what's them added together?
21. No, I'm just kidding. 3.
Cool.
You had me at 21.
Okay, do we see, like, how can we generalize then this in a way so that we don't have to use actual numbers? What do we want to say, like f of x for any Fibonacci number? So how could I type this. What would I put in here in the middle as the argument?
X minus 1 and X minus 2.
Right. Great. So we came up with our formula here, and this is basically what we'll use for a recursion. Exactly. So okay, so we're gonna implement this recursively. So let's do const fib. We're gonna take in n. So we know that if we call f 0, which will get 0. If we do f of 1, we should get 1, and so on and so forth. 2. Okay. So what would be the edge case for, any ideas for the edge case for this recursive algorithm?
I believe if n equals 2, we return 1.
Okay. So if n is equal to 2.
Isn't 2 correct though with the algorithm? I mean, is 2 not f of x minus 1 and f of x minus 2?
Yeah, you're right. So if it's 1, we return 1.
Okay, that sounds good. And if it's 0, what do we return?
0.
Right. So these are our starting values, sort of. These are our starting values. They happen to be our base cases as well. And from here is where we're going to build the rest, basically. Okay. Then we know that the nth Fibonacci number will be equal, or in this case, x, will be equal to the sum of the previous one plus the sum of the previous one. Any idea what I should type here from what we saw?
Let's call on Johan with these really cool headphones. What kind of headphones are those? Those are cool.
Joanne, you're in mute. I'm not sure.
You're muted, Joanne. Oh, thank you. What should we type, Joanne?
What was that?
I think she's talking to her roommates.
I'll stop.
What should we type here, Joanne?
Sorry. I guess in this case, we probably need to I think we need a loop.
We wouldn't need a loop. Let's see. Any other ideas, anybody else?
We return fib of n minus 1 plus fib of n minus 2.
Right, look at the function on line 6, Joanne. Do you see that?
Yeah.
So that's kind of the beauty of this algorithm, is that it's like by definition recursive, right? Any Fibonacci number is defined by the value of some other Fibonacci numbers, right? And those ones are defined by the values of some other Fibonacci numbers, and so on and so forth, all the way down to basically 0 and 1. 0 and 1 are the only ones that aren't defined by that function. Does that make sense?
Mm-hmm.
So wait, Joanne, can you help us finish out? What should we write here?
Fib, and then n minus 2.
Got him. Nailed it. All right, so let's run it and let's see how it performs, Alejo.
Yep. So let's take a look at this console log.
You should put a you should put like a, here's what I would do, Alejo. Maybe actually I could just do it myself. You should write a little function. I can just do this, right? Because I can go to this REPL.
Yeah.
Here, I'll do it for you. While you write this out. Basically, what we want to do is we want to time. Oh, I don't have it. Apparently, I don't have a REPL account.
Let me share it again.
No. I just don't have I can't log in. I need like some Google. I'm gonna log in with Google. Okay, I'm logged in, folks. Liggity, logged in. Okay, so let's switch.
So basically, if it's equal to 0, then we return 0. If it's equal to 1, then we return 1. Otherwise, we just return whatever number as long as it's greater than 0 and 1.
So we'll return what you call whatever number will be whatever number will be equal to the previous number, whatever that is, plus the previous number. And then we'll see a visualization of the tree, of the recursive tree, that can also help with this and why we will want to optimize this. Cool. Oh, Ben, you want to do the timing?
I'm Googling shit because I don't know how to write JavaScript, and nobody does. And you just always Google. Don't be afraid to Google.
You mean like you want to take the time before and after, right?
Exactly. I just want to do. Here we go. I found it. So basically, it's like start. We don't need that. This can be a const even, right? We're gonna do it, and then we're gonna say, we can even actually do this. We can be like took, right? I think we can do like that, and then we can be like start, or it's like new date minus start, right? Which is apparently going to be in milliseconds, right? So if it's in milliseconds, then that means we want to multiply it by 1,000 to get seconds, and then we want to put S at the end. Right?
Isn't it dividing by 1,000 to get the second?
Yeah.
Yeah, good call. So yeah, so instead of doing console log fib, do log fib perf.
Cool.
And we would say like, we can even be like fib of, and then we could be like n. Just trying to make it neat for y'all, you know? I know y'all like it really neat, right? Everyone likes really neat code. Look at how neat I made it, okay? I did my best. So this is just a very simple utility function that you could have it take a lambda so that it's generic. But right now, this is specific to Fibonacci. So instead of calling Fibonacci, you just call this function. It does the Fibonacci, right? You can see it doing the Fibonacci here on line 16. But more importantly, it sets a start time and then logs the end time. We might actually want to do it like this. You know what? Let's do it like this. This way we know that that like the Fibonacci sequence is happening before the console log, because console log might start log. You know, you never know how it works. Like you can never be too sure about like how the programming language is going to evaluate. Maybe it evaluates the last argument first or something. I don't know. It probably wouldn't, but you never know. So yeah.
Yeah. Something I just thought about is that JavaScript implements, or the engines implement some optimizations that we had to disable the other day. We wanted to do something similar to this, but let's try it out. So
we'll see.
Let's run this. So we have 0, 1, 2.
You don't need these console.logs on line 21, 22, 23. Because
cool.
log fib perf doesn't return it, right? It's just gonna log.
Mm-hmm. Okay. Let's take a look. Oh.
Uh-oh.
Just
like always. Line 23. Oh.
Oh yeah, there's an R in perf.
Perf?
Line 23. Down to 23.
Wait. Oh,
yep, there you go.
Yeah.
Try again. Ooh. So maybe don't divide by 1,000. Just get rid of that divide by 1,000 and make it MS. Yeah, just make it MS.
Mm-hmm.
Yeah, you put that print back though. You got rid of the print. Yeah. You don't need it, but why not? Okay, so it's fast.
So
let's try some bigger numbers.
Let's try some bigger numbers. Let's actually see. Let's just go. Let's just try to see this. 3, 4. And what do we expect? The fourth is 3, 5,
3, 5, 8, 13, 21.
Okay, let's run this. Yeah, so I think this is the optimization that I'm not sure.
Oh, is JavaScript doing memoization under the hood of Lambda calls?
Maybe.
No, I think it's not. Try like 27. You know, try like one bigger, right? Yeah.
So like 25.
Yeah, do 25, 26, 27. Yeah, exactly. What you should see is that the jump is going to grow a lot every time. It's going to grow exponentially, right?
Yeah. So under the hood, there is something going on. Let's see if we wait. Let me copy this.
Crazy. That's crazy. So what is that? Yeah, do it in npm.
Yeah, that's. But even still here, we have to do some stuff. Yeah.
Whoa. So is JavaScript performing memoization? It's seeing like, oh, I've evaluated fib of 22 before. I'm going to just return that same value.
I think there's something like that going on. I don't know exactly what it is, but I remember.
I mean, do you want me to add like some bullshit in there for you? So like one thing you could do is just to trick it, go back up to the fib code.
Yeah.
I don't know if this will work. I just did an experiment. Scroll up to the top. So yeah, right here, put an if statement. And be like, if what's the JavaScript rand?
The JavaScript what?
Rand, like random. How do you do random number?
Oh, math.random.
Yeah. So what does that give you? Just a totally random, like floating point between 0 and 1.
Yeah.
So it'd be like random times, do like times of 10,000 or something. And then be like, if that number is equal to 0. You know what I mean? Like
have it do some work.
or if it's less than 1 or something, right? You're like basically something that could possibly be true.
That could possibly be true.
Console log, like, whoa, it happened, console log something or something, right? And what will happen is very rarely will be, I mean, there'll never be less than 0, right? But it's like, yeah, maybe triple equals 0, which is technically possible, right?
Yeah.
And then you should put like a console log. You should put something in there like console log or something. Yeah. Like, whoa.
But I think that's gonna pollute the terminal. Oh no.
No, because it never happens. It's very unlikely. It's 1 in a 100,000 chance.
That makes sense. Yeah, let's
so do. Like, did that fix it? Did it give you a good?
No.
No. Wait. Put some text in there. I want to trick it. Yeah. And then run it.
Still some fancy stuff. Disable optimizations.
That's crazy.
I look at this and there is system stuff that I need to do. Yeah, never optimize. This is like an instruction for the status.
Yeah. What is that percent? I don't know. Maybe no space. Maybe put no space.
Did it? Oh.
I don't know. I've never seen that syntax before.
This is for like some instructions for the V8 engine.
Yeah. Where does it live? Let's see.
Oh, some people suggest a try catch. Oh, I think I need to do this. They allow native syntax. Here, I think we have it.
You got it?
Yeah.
Okay. It's a compile time directive. Okay, cool. So try 28, try 29, yeah.
Let's take a look.
Whoa, look at that, dude. Look at that. It starts to get really slow. The difference between 29 and 30 is almost double. Okay?
Mm-hmm.
So, Owen, why is that? Why is the difference in performance between Fib 29 and Fib 30? Whoa, Jesus Christ, I'm not sure. The difference between Fib 29 and Fib 30 double. What do you think, Owen? Mr. Jones.
Jones.
What's up?
I think because I'm not really sure. Something to do with like the log. I'm not sure actually.
Kathy Puma, late addition to this team. Welcome to the team. Welcome to the squad. How you doing? Why do you think the performance between Fib 29 and Fib 30 is so significant? It was instant to do Fib 7, Fib 8, even Fib 25 was only 18 milliseconds, right? But just adding one number from 29 to 30 took more than every single Fib before it. Fib 28 was even, it took more than, like, Fib 28 is about 70 milliseconds. But it took about 70 more milliseconds to just do one more than 29. Why is that, Kathy?
I'm not sure.
Let's look at the code. Let's scroll up, Alejo, and let's look at the code, Kathy. So let's look at this fib function. Do you see that fib function on line 8, 9, 10, 11?
One, 10, 1, okay. So n equals 0, return 0. I'm not too sure.
Maybe.
So how long does it take? Let's say that it takes like, we see that it takes, fib 29 takes 100 milliseconds, right? Right?
Yes.
So we assume fib 29 takes 100 milliseconds. So when you do fib 30, it's not 0, right? It's 30. It's not 1, it's 30. So you do a line 11, right, Kathy?
Yes.
So what are you doing on line 11?
Returning. You're doing recursive, so you're doing fib n minus 1 plus fib n minus 2. So you're doing
Yeah, so what's n?
30,
So what's 30 minus 1?
29.
So you so say exactly what you're going to do on line 11. You're going to do fib of
Fib 29 plus fib 28.
So how long does it take to do 29?
109.
And what long does it take to do 28?
69.
And what's like 109 plus 69 added together is about 170, right?
It's 178.
Right. So it's a little bit faster because the truth is that these numbers can't really be, you know, I mean, like it's your
so
computer
small.
is doing a lot of other stuff. You're doing Zoom, you know, you're doing all kinds of things. So your CPU is not dedicated to JavaScript. So, you know, things are going to vary in terms of how long they take. But does that make sense, Kathy? Then why does fib 30 take so long? Does it make sense?
Yes, it makes sense.
Because so explain it back to me, Kathy. I want to hear it.
Because when you do fib 30, it does line 11, and in line 11 you're returning fib 29 plus fib 28. At fib 29 it takes 109 milliseconds, and at fib 28 it takes 69. You add it up, it's close to 167.
Exactly. So that makes sense, right? So before you said you didn't know, but now you know.
Yes, 9.
Good job. You figured it out. Okay, so I'll take you off the spot, Kathy. Who haven't I called on yet? Vanille, Joey. Whoever unmutes first gets to go. Whoever unmutes last gets to go. Oh, it's Vanille. Joey unmuted first. Good job, Joey. Waited, nose goes. All right, Vanille, sorry, but you were slow on the draw. What could we do to make this faster? Why is this a stupid implementation? Let's just be real. What is dumb about this?
Based on the topic that we're doing today, what's dumb about this is the fact that we're I guess we're redoing things every time. So we're redoing when we do fib 30, we're redoing fib 29, fib 28. So what might make it faster is we store the result of the I guess the lesser the sequence of fibs. Like, so store what fib 28 and fib 29 is. We could just add those values that's already been seen.
So how many times are we computing fib 29?
We're computing fib 29 twice.
I don't think so. I think just once, right?
Yeah, once. We're computing it once.
Just once, right? So
Yeah.
how many times are you computing fib 28?
Once.
Mm-mm.
Or twice. Twice, because there's from fib 30 is fib 28, but then from fib 29 there's fib 28 and then fib 26.
Seven.
So if we store that fib 28 has already been seen, we can just re-grab that value, and then from fib 26 we store from either fib 28 or fib 27.
Yeah, and it doesn't
Re-grab
matter.
that
Honestly,
value.
it doesn't matter what the order is, right? It just doesn't matter because, well, let's move forward a little bit slowly though. So 29 happens once, right, Vanille?
Yeah.
28 happens twice. How many times does 27 happen?
27 happens 3 times.
Is that right? 27 happens.
From fib 28, if we don't store it.
It happens 3 times, you think?
From fib 28, it happens once. From fib 28 minus 1, fib 27. It happens fib 29, minus 2, 27, and fib 28, minus 1, 27 again.
That sounds right. That sounds right. So 27 happens 3 times. Once from the 28, once from the 29, and then once from the other 28.
Yeah.
Right? Okay, what about 26? How many times does that happen?
That happens 1, 2, 3, 4 times.
Right? So are you seeing this exponential growth? Right?
Yeah,
You're
it's
seeing
doubling.
exponential growth, right? It's like we're doing fib 29 once, but 28 twice, but 27 3 times, but 26 4 times. Right? We're doing them over and over and over again. So memoization is going to solve. It's not just going to make like us do half as much work. It's going to make us do way less than half as much work, right? Because we're going to do 27 only once. We're going to do 26 only once. We're going to do 25 only once. So let's implement the memoization.
I want to reiterate that, maybe on a smaller sort of example, or just say in a few different words. One is if we take a look at even this is a good example actually. We see that basically we have repeated calls. We see that the algorithm will go depth first on the left side. So our function will basically, if we were looking at the call stack, it would be f of 30, and f of 30 will put on our call stack 29, and 29 will put on our call stack 28. 28 will put 27, and so on and so forth until we reach f of one of our base cases, so of 1, right? And those will, after we reach our base case, then the recursion stops, and we start sort of by going, the call stack starts going back down, and so that's that. The idea is that at some point, when we were going down here on the left, we computed the result for f of 27. And the idea is that we're going to save that value, the result of f of 27, because it turns out that we do it here again. We do it here again, for instance. And we shouldn't have to compute it again. We should just remember the first time we did it here. Remember the first time we did it. And instead of this having to have like another set of branches here, this is called like the recursion tree. Very helpful visualization for any recursive algorithm. Instead of this 27 having a subtree down here to compute it, because that tree will be exactly the same as the one we have here, let's just remember the value of the first time we did that f of 27. And whenever we try to do it again, we'll have the result. We'll have the result. We don't have to go down, do the recursion. And that, what we're about to do is then memoization. Actually, and I wanted to pull out this definition that I found very helpful. Let me clear this here. The definition that I found helpful was this. So this is a question that I had. What's the difference between, oh, what's going on here? What's the difference between memoization and dynamic programming? And I was thinking that maybe there's no difference. Maybe you can use the words interchangeably, but I think this kind of gave us some context on that. So basically, memoization, in computing, memoization is the optimization technique used primarily to speed up a computer program. By having function call, avoid repeating calculations of results for previously processed inputs. So that is memoization. And dynamic programming is in mathematics and computer science is method for solving complex problems by breaking them down into simpler sub-problems. Basically, this is what we talked about when we talked about recursion. I would imagine it's safe to say every recursive problem that is breaking down a problem into sub-problems is dynamic programming. And most recursive problems are actually doing exactly that. I actually can't think of one that is a recursive problem that doesn't have to do with sub-problems. Actually, Ben, do you know any of those? Like a recursive algorithm that doesn't operate on sub-problems? Because I think that's kind of so key for recursion itself, the sub-problem.
Yeah, it's very definitional, right? The definition of recursion is to say, hey, I can call myself with a different input and use the result of that to get an output, right? That's like what recursion is. Well, another way of saying that is, oh, I can use this function to, or rather I can divide this problem up into a smaller subproblem, which is actually the same problem, right? With a smaller input, and take the result, combine it, and get my ultimate result, right? And so by definition, if you're using recursion, then you are dividing it into a subproblem.
So is it safe to say then that all recursion is dynamic programming?
I don't know what dynamic programming is exactly. It's like, to be honest, it's something that I've literally never done outside of school.
Based on this
I've never done it at my job. Based on this definition. Okay. In computer memoization is an optimization technique used primarily to speed up computer organizing function calls, avoid repeated calculation of, yep. Dynamic programming is a method of solving complex problems by breaking them down into simpler subproblems. Yeah, I think basically this is a very vague definition because dynamic programming is very vaguely defined. Dynamic programming is a specific strategy of using the standard practice of like breaking down a problem into subproblems to solve non-polynomial problems. I think that's what dynamic programming is, because like a lot of things are not dynamic programming that are methods for solving problems by breaking them down. So I think keyword here is complex. It doesn't feel like it's an important word, but it is. So the difference between dynamic programming and regular programming is that these problems are complex. And that is like, that's like a technical term, right? Complex is not the technical term, but what it's referring to is the technical term, which is these things called NP complete problems, non-polynomial complete problems. Examples of these are like the traveling salesman problem, the bag stuffing problem. These are problems that there does not exist a solution where you can definitively solve it in polynomial time. You have to try like everything, every possible combination. But instead of trying every possible combination, you can often weed out shitty ones. That's one strategy. And another strategy is you can often notice, oh, I've done this problem before, like the Fibonacci one, where it's like, oh, in Fibonacci, you have to compute the Fibonacci of every Fibonacci before it. You have to do it. You can't get away without doing it. But you can speed it up by saying, wait a minute, the Fibonacci of x and the Fibonacci of x minus 5 actually have a lot in common, right? They have a lot in common, in fact, because the Fibonacci of x minus 5 is included in the Fibonacci of x, right? And so that like kind of logic is like a mechanism of improving the performance of your naive solution, which has to compute every Fibonacci. But in the end, you still compute up Fibonacci. So that's what makes it a complex problem. And there are much more harder complex problems. So there are, like, basically think about like a graph traversal. That you are breaking the problem up into smaller pieces, but it's not a complex problem. And so it's not dynamic programming. Does that make sense, Alejo?
I think sort of. I think like I haven't done a lot of graph stuff myself, but I think I understand. I get a glimpse of what you're talking.
Right. So it's like think about it like here are the tools. Like you should think about it like these are tools in your toolkit, right? So recursion is a tool in your toolkit, right? Breaking a problem up into subproblems is a tool in your toolkit. When you use recursion, you are using that second tool. It's like, think about it like breaking it up into small problems is a nail, and recursion is a hammer. It's like you can hammer stuff, but it's not really that useful. Most of the time you're hammering nails, right? Most of the time when you're hammering nails, you're hammering subproblems, right? But you can use other things to use nails. You could have a nail gun, right? There are other ways to break things up into problems. You can break things up into subproblems using iteration. You can have an iterative solution that breaks it up into a subproblem. Look for iterative solutions to merge sort, for example. Or like iterative solutions to quick sort. You know, there are non-recursive quick sorts, but those are breaking up into subproblems, right? Okay, and so those are like two different tools. And then memoization is another tool, right? And you can use memoization when you do recursion. You don't have to, but oftentimes you do. Oftentimes the programming language does it for you, like we saw with JavaScript, right? JavaScript's doing memoization for you because it's like, I got you, buddy. You're doing recursion and you're calling the same function over and over again 1,000,000 times. Don't worry, I got you, right? So it's a common solution. You don't always need it, but like it's something that's another tool. And then dynamic programming is using those tools to solve really fucking hard problems. You know, and I think like a good example of a very hard problem is the bag stuffing problem. Do you want to search bag stuffing? Bag stuff problem? Bag problem? Yeah. Yep. Maybe not stuffing.
Stuffing sacks?
Yeah. Maybe it's stack. Yeah, I don't know. Hold on, let me Google it. There's a Wikipedia entry on it.
Like
the knapsack.
Knapsack.
Yeah, knapsack maybe. Yeah, maybe that's what it's called. Yeah, knapsack, dude. That's the one. Go to the Wikipedia for knapsack. It has a nice kind of image to describe it. So look at this image. Okay, so we're not going to solve this problem because this problem is crazy fucking hard, and I don't even know how to solve it really. And we can like kind of talk, and it would take me like an hour or two to figure it out. And so I don't think it's like super useful for me to do that in front of you. Or it's useful for any of us to figure it out right now. But I think it is useful to understand the scope of what these kinds of hard problems are. They're called NP hard. NP hard, that stands for non-polynomial hard. And that's a technical term. It's saying this problem is so hard that we cannot solve it in polynomial time. Polynomial means like x squared, x cubed. That's a polynomial. But 2 to the n is way bigger than x squared. Right? So like if you Google right now, like what's 100 squared? Right? 100 star 2. Yeah, it's like, it's big. It's 10,000. What's 2 to the 100? It's some stupidly big number. It's so much bigger. It's like a billion, trillion, bajillion times bigger, right? This is saying that this is 1.2 times 10 to the 30 zeros, right? So it's like 1,000,000,000,000,000 30 times. That's how big this number is, right? And so these NP hard problems mean they for inputs of size n are like this big, right? If n is 100, their result is like fucking huge, without things like memoization and things like that, right? Like the search space. So anyway, so let's go back to the knapsack problem. It's a quintessential NP hard problem. So let's think about this problem. What is this problem? This problem is saying, if I have a bag that fits 15 kilograms, right? And I have a bunch of different goods, some of which are 12 kilograms, some of which are 1 kilogram, some of which are 4 kilograms, some of which are 2 kilograms, etc. What is the best way to fill this bag up so that the amount of stuff in the bag is the most amount of money, right? Because the 12 kilogram thing is worth $4, 1 kilogram thing is worth $2, 4 kilogram thing is worth $10. I mean, this is actually a really easy example. You just fill it full of 4 kilograms, right? Right, because those are worth a lot of money. But like, we could come up with a example where the numbers are really hard to solve that problem, right? And I think we were dealing with this earlier last week when we had a problem where it was like, what's the best way to make change, right? Do you remember last week we were talking about this? I feel like we were, right? Weren't we talking about this last week? Am I misremembering? And it's actually the same problem, like from a high level. Like a computer science professor would be like, oh yeah, these are the same. They might have some subtle differences, but like they're fundamentally the same kind of like combinatorial optimization problem. Right. So anyway, let's scroll down a little bit to computational complexity in that Wikipedia entry. If you look at the computational complexity section.
Oh, I think the link is broke. Oh, okay.
So it's basically saying like, this is like, it's going to be a lot of jargon in here, but the important thing is it's NP complete, meaning there's no known algorithm that is both correct and fast in all cases, right? So remember I was saying NP hard, there's also this thing called NP complete. So this is the like, you know how like physicists were working on the Higgs boson for like years, right? For like literally like 50 years, there were physicists that were like, does the Higgs boson exist? Does it exist? I don't know. We think it exists. And they recently proved it. It was like the biggest breakthrough in the history of particle physics in like the decade, right? Since Einstein. So if you look at that NP complete graph, there exists a computer science problem of that scale, which is currently unsolved, which is P equal to NP or is P not equal to NP? Meaning, are there problems which are NP hard that are not non-polynomial complete? Like basically, like are these sets disjoint or joint? And it's a very complicated problem because nobody knows the answer. It is an unsolved problem in computer science. So it's really cool, it's really exciting, it's really interesting. The thing that's relevant to you is to understand like there exist problems out there where we have not figured out a fast solution that is correct. We as humanity have not figured it out. And the bag stuffing problem is one of them. And if we could figure out a solution to it, we could prove that P is equal to NP. And if we never do it, we could potentially disprove that P is equal to NP and thus prove that P is not equal to NP. But since we basically just don't know if the solution exists, we haven't found one yet, we can't definitively prove either way. So that's kind of the state of like NP hardness. This is a very, very like fun and academic topic that has very little bearing on my day-to-day as a software engineer. It has basically no bearing at all.
Let's
yeah,
get back
so
to
anyway,
the
it's fun to talk about.
normalization. Thank you for that. I think I had come across something like this on the solving a Sudoku, and I don't remember exactly where Sudoku is really easy to check if a solution is correct, but it's really easy to write an algorithm to check if the solution to a Sudoku is correct, but it's hard to write. I think it's hard to write an algorithm that finds that solves the Sudoku. It's easy to check that for a given answer, whether it's correct or not, but it's hard to write an algorithm that solves it. Is that some of what you were talking about, Ben? Like with NP and MP, where I think you're in mute.
I'm sorry, I wasn't super following. What do you mean is it the same thing? You're saying whether or not the compiler, this is referring to the fact that the V8 engine has memoization optimization built in. I guess what's the relationship with NP? I'm sorry, I'm confused.
No, I was just sort of remembering back to something I came across, which is writing an algorithm that checks if a solution for a Sudoku is correct versus writing an algorithm that finds the correct solution for Sudoku.
Yes, that is related. It's not the same thing, but it's adjacent to the NP problem, where it's like, that's a lot of how encryption in the internet works. Like in the top left of your browser, you see that little lock, right? You see that little lock, and you can click on that lock, and it will tell you like you're secure. It's like, how does that work, right? That works because coming up with like really giant prime numbers is really hard, but validating that a number is prime is really easy. And that's the same with Sudoku, right? It's like coming up with a solution, you got to search all the search space to figure out what are all the different possibilities and try them all out. But to validate that it works is really easy. Either it works or it doesn't. You just check it, you know? You don't have to check everything in the world. You just have to be like, if all these columns work, if all these rows work, it works. This prime number is like, if it's not divisible by like these large prime numbers that are like, you know, up to all the prime numbers that are up to half of it, and we have specialized hardware to do it, then we know that it's prime. And so that's how these like this SSL connection security works, is that very large prime numbers are generated on the server, and then they use those numbers to encrypt your traffic. They send it down to you, and then you validate that the prime number they use to encrypt it is indeed prime, and then you decrypt it with your own like paired decryption key that they provide. Like you have a handshake where you give each other your decryption keys. And if it was really fast to discover these prime numbers, anyone could just create decryption keys. But since it's very slow to come up with them, the internet is a secure place. So that's I think a more adjacent problem to the Sudoku one you're describing. But yes, those are NP problems, right? The SSL encryption relies on the fact that there is no polynomial solution to creating arbitrary decryption keys for like RSA, what is called like these prime number RSA tokens. Anyway.
Cool, so let's implement the memoization for this, basically.
Yeah, that was like a lot of random information. It's like fun to talk about, but like I stress, if you're not following, don't worry about it. But you should be following this code, and you should know about memoization, you should know about recursion, subproblems, that stuff you should know. NP, prime numbers, all of that stuff, dynamic programming, doesn't matter. It'll never affect you.
Cool. So the point of memoization, as we saw, is to optimize the running time and avoid duplicate work. So the way in which we'll do that is, what happens then? What happens if we have here something that we can call, let's have an array here. So an array, let's call it memo. Let's have an array outside for now in the global scope. We'll call it memo. What we'll do is that once we calculate the value for a given Fibonacci number, we'll store it in this array. We'll save it there. And the next time we try to compute a number for a Fibonacci number, we'll check if it's in the array. And if it is, then we return that. If it's not, then we go ahead and keep with the recursion. So what if we do something like this? Let's say result, this res. Yeah, actually.
A random question. Isn't it better to store it as an object where the key is the number and the value is the value, like to find it easily?
Yeah, saying the same thing. Return the key, the value.
Yeah, it will still be the same thing, because we see that the sequence starts at 0 and 1. So we could use the indices to key into those pieces of the array. So it will be the exact same thing. In fact, yeah, we could do this. Let's put 0 and 1 here because we know that that's how it starts. And let's do if and wait, hold on a second. Let me take a look here on my reference. All right. Yeah, I think actually this, we'll need to create an array. Let's do it with an object. And then maybe we can see how we do it with an array. Okay. So what we'll do is then store it in there. So we'll say memo n, or on that key, let's put the response. And before that, we'll need to check if we have already calculated the Fibonacci number for n, return the Fibonacci number for n. So basically something like this. And lastly, return list here. Okay, let's try this out. Look at that, how fast that is now.
Woo!
So it's from 167 milliseconds to nothing basically. You know, it does take some time, but for the computer, it doesn't even register. But the idea is that it's really fast. Let's take a look at this. Let's take a look at, let's console log here the memo. Let's console log it after we have it right here. Actually, this might be a bit too much effort. Let's do it for a small number. Let's do it for 7. So now, actually, what was, we saw 27. Let's take a look at this. So, and then let's walk through it. So I'm gonna do, let me annotate here. So we say that f of 7 is gonna be equal to f of 6 plus f of 5 and actually, sorry, plus f of 5, and then f of 6 is f of 5 plus f of 4 f of 4 f of 3. I think it's, I want us to see this basically. So actually, even I shouldn't even be going on the right side. Let's do it. Let's finish it here. 4 plus 3 3 2 2 and 1. This is 1 and f of 0, right? And then here we reach our base case where f of Fibonacci of 1 will be 1, and Fibonacci of 0 is, what did we say here? 0. And let me stop. Okay. Right, so basically the recursion goes all the way to the left first, until we reach f of 1, until we see that first one. Therefore, wait, hold on. We see 2 is the first thing that gets added. Yeah, okay, yeah, that makes sense. We go all the way down. When we all on f of 2, we are gonna calculate f of 1 and f of 0, and we know that those will return 1 and 0, right? And then what we do is we save that result. So the result for f of 2 is 1, right? Because it's 1 plus 0. So we know now the result of 2. What we do is we put it in the object, and we see that in here. The result of that was 1. Cool. We have that one. Then we go back sort of to this area here on f of 3. We have the result for f of 2, and we saved it into the hash table. We calculate the result of f of 1, which is 1. And then that will result on 1 plus 1, 2 for f of 3. And we see that that is the next value that gets added onto our hash table, onto our object here, the value of 3. The result of that is 2. Then we go back to f of 4 here, and we saw that we finished on the left side. We computed the value for f of 3. And the right side will be f of 2. But it's not going to go do that math for those because our function here says checking the memo object. In that case, when on the right branch of f of 4, we call it with 2, we check that, and that is already in our memo. So how long does it take to get something from a hash table?
Instant.
Constant time. Great. So that is.
Don't say instant, right? Say constant time, because those aren't the same.
Oh wait, did I say instant or?
No, Amin said instant.
Oh, I say constant time.
Right? Yeah, you said constant time, but I think Amin said instant. Technically it is instant in effect, but it's like it's not something, in the interview it's fine probably, but like just they're not the same.
I guess constant is that no matter how the input is, it will always take the same amount of time. Okay. So on the right side of F4, we already calculated F2. We calculated down here. We shouldn't go a calculator again. We just access it from our memo object, basically. And then that's the same for the branches of a 5. We have the result of 4, and on the left side, on the right side, f of 4, we already have it in our memo, so we don't need to go down there. And basically, then this is memoization. This is the basic principle of it. Store results for repetitive operations. Remember them so that you don't have to calculate them again. And I think there was something here that I wanted to look at. Yeah. I think it's something hard to see, but when breaking a problem into smaller, simpler subproblems, we often encounter the same subproblem more than once. So we use memoization to set the results of previous calculations so that we don't have to repeat them. So Give me a thumbs up if that makes a little bit of sense on what we have here. Okay, so 2, 3, 4. Questions or thoughts that you have? So this approach that we see here is in dynamic programming is known as the top-down approach. Yeah, I think I have in the cracking the code interview, it says the top-down approach. The top-down approach can be more complex since it's less concrete, but sometimes it's the best way to think about a problem. In these problems, we think about how we can divide the problem for case n into subproblems. So that's a kind of very general. But let's compare it to the bottom-up approach for this problem, and then I think that will give us an idea as to why this is top-down and bottom-up. And it's sort of something, you know, how the recursive tree kind of goes down. That's the way that I sort of like see it or think about it. Like this is going down. The bottom up is we start from the bottom and we'll go up, and we'll see what that means. Okay. So this is using this like external variable. That will be a side effect. I think it will even be a side effect, but the way that you most commonly can do it is to pass it as a second argument. Pass the memo as a second argument to your function. Something like this. And then we'll call it. Passing in an empty object. It can also be an array. Anything that you use to remember the work that you've done. Let's oops. Cannot. Oh, right. That's because we were using the one to log the performance, so we saw that. Let's do video. Okay, we got 13. Great. I was thinking, yeah, we could have done this, yeah, with the index, as well, with an array. But I think, yeah, what if we do this 0, 1? This should work. So because it just happened that the 0th Fibonacci number is 0, the first is 1, and so on. So it doesn't matter if it's an object or an array in this case, because it just happened to be that the keys match exactly with our index, with our indices as well. And in fact, we could get rid of one of the base cases here, because 1 is already in the array. In JavaScript, if we check for this one, since 0 is a falsy, we wouldn't be able to do this one yet. Okay, so this is the top-down approach. The bottom-up approach will be, we know where we start, and when we go up to that number, and that will look something like this. Yeah. So this one will not be recursive, but then this is still dynamic programming. Let's take a look at this. Oops. Let me clear this screen. So this could be bottom up. Oh no, this is top down. Down approach. And generally, all these it seems that all these problems have those two approaches, bottom up and top down. So the bottom up approach. Let's do this. Let's call this. I will call this fib 2. Fib 2. And the question here, or what we want to do is, what if we have an array with the first two Fibonacci numbers, and just go iterating from those two, adding the next one, calculating the next one, then just repeat that, the two earlier ones, to calculate the next one up until we get to the number that we want. I think let's just look at it, because I feel like explaining it it's a bit complicated, or at least for me. Let's do something like this. We'll still need to have our cases. If n is equal to 0, return 0. If n is equal to 1, or 1. And what we will do is we'll create an array. And actually, in JavaScript, we don't need to do this. We just need to, let's call it, oh, they actually called it memo here as well. Let's call it memo. Like this. And then what we do is just loop. Oh, actually, we put these two right there. We can put the first two cases. In fact, we need to put the first two cases on. And then we can just loop for let I 0 while I is less than, well, I is less than n, is the I plus plus. And we can just do memo dot push memo. Oh, actually, we don't start at 0, we start at 2. Memo that push I minus 1 plus memo I minus 2. In the end, then we can just return memo at n minus 1 plus memo n minus 2. So here, the idea why it's called like bottom up is because you start from the bottom, from the beginning, and make the sequence up until the number you want. So it's let's see if it works first. 2, and we don't. Actually, I'm not. Let me comment this out. Bring this closer here. And run this. Oh, we got 13 exactly as we expected before. If we do the performance, we'll see that they're actually the same now. Right. Oh, undefined. Fibonacci to chain, where is that undefined coming from? Oh, right. This is because I don't know. I no longer need to cancel out here. And even if we do, which one was like 30? That's the answer, and it took almost nothing, or nothing. Okay, so this is the bottom up approach, and this, according to cracking the code interview, still considered dynamic programming. So most of these problems have those two approaches, like top down and bottom up. Questions or thoughts about this one? Do we get like a general sense? Give me a thumbs up if you get a general sense of how this is working. Okay. Okay, so I need a question from anyone that did not do the thumbs up. Let's see. Owen. Or what part can I re-explain? I mean, are you okay?
No,
Yeah,
understand.
it's my phone playing.
Okay. I thought you ran out of electricity or something.
No, he's playing with the flashlight.
Sorry, go ahead, Owen.
Oh, wait, can you explain the why it's like why it's so much like the time complexity again?
Right. So this the time complexity of this will be O of n, or linear time. Because how many calculations do we have to do? If I pass in 7, how many calculations are we doing?
Oh, 7.
That's correct. We have 30. We are doing roughly 30 calculations. We're doing 30 minus 2. Right. This, as we saw, the numbers on time complexity were growing exponentially. Actually, the time complexity of this without the memo is it has some nuances. But I was reading top down without memo will be 2 to the power of n, and there was some discussion about that this is why is this doing that? 2 to the power of n, which makes it exponential, which is really bad, and that is because we were doing a lot of repeated work. The repeated work makes sense when we were doing that. Owen. What was that? Do you see the repeated work that we were doing and how we optimized it? Does that part make sense?
Yeah.
Okay. So that repeated work elevated our time complexity to be 2 to the power of n. And this is roughly, like, the way that I think about it is when we don't have a memoized function, each call, well, we end up with n levels in the recursive tree, right? I think I can't go back in time because I was doing the drawing on the screen, annotating on the screen. But we if we draw all that tree, we'll see that we'll end up with n levels, basically, and each node in that, each node of each level will be branched into 2, and then that is exponential, basically. That's the way that I think about it. As the n will ended up being the number of levels in the recursion tree, and the branching factor was 2. So each node will branch off into 2. So that was really bad there. Then once we optimized it with the memo, we go back to O of n. And I think it's, yeah, there's some numbers here that I thought doesn't really matter. Actually, I don't remember if it's, actually, Ben, do you remember here? Is it just, I know they will be just O of n.
Yeah, that's right.
But I guess I was trying to account for the, yeah, for some of the other stuff, the other calculations that get made.
Yeah, but they're all constant, right? So it's like O of n times 3 is just O of n, you know?
Say that again?
Like, if you have an operation that's O of n, and then you make it go half as fast, it's still O of n. You make it go a tenth as fast, it's still O of n, right? Because even if it's a tenth as fast, if you increase the number of inputs by 1 billion, it just goes slower by 1 billion, right? It's like maybe it's 10 billion, but it's still just a factor of 1 billion. Whereas like if you have some other function like n squared or 2 to the n, 1 billion is a lot more than 1 billion, right? It's like, you know, some huge number. So when you say the other functions, you probably mean like on line 21 and 22, like the if statements. Those are all constant though, right?
Yeah, I do know that.
Even the loop is constant, right? Because the loop is just, oh no, this loop is not constant. This is just a non-recursive way of doing it, right? This is just a non-recursive loop. Yeah, and so this loop is just linear time, and the body of the loop is 2 linear time operations summed together, which is all linear time. Linear plus linear plus linear plus linear is equal to linear, right? And constant plus constant plus constant equals a constant. So this is like a linear operation where the operation is constant plus constant plus constant. So it's just constant times linear, which is. So you were right the whole time.
So yeah, basically here we're not doing any of that repeated work that we were doing before. Other questions or thoughts? No other questions or thoughts?
I have a question about the space complexity. Is it the same thing with the memo or without the memo? Since like kind of the memo is taking kind of the stock.
That's a good question. So the recursive will be, it will be O of n in space complexity. O of n in the call stack because of the call stack, and our array, our memo will potentially also be have as many elements as well. And here the array will also be O of n. And let me double check that because I think that is actually explained here. Well, actually maybe not. Yeah, no. It is not talked about here. But it will be linear unless Ben wants to add anything or correct me there.
You're talking about space. That was the question, right? I mean, was like, is there a space? And so this is like a really key part of a common interview tactic where they're like, it's faster, but are there any trade-offs? And they're like, yeah, I see where you're going. The answer is space complexity. And absolutely, memoization takes up more space. That's true. but it's usually pretty small, and that's why like V8 just does it in there. And like computers have a lot of RAM now, you know what I mean? And so like you may have noticed that Chrome is taking up a lot of RAM. There's a lot of memes about Chrome gobbling up your RAM. It's not because of the memoization, but that's part of it. You know what I mean? If you turned off that memoization, websites would run slower, but Google Chrome would take up less RAM. So it is very much a trade-off, but a trade-off that generally people are citing on the side of take as much space as you want because space is free and time is expensive. Time is money. But yeah, you know, like it is true though that you take up a lot of space with your deep stack though. Like your recursive solution takes up a lot more space than your iterative one, because your iterative one is not taking up any space except for the memoization. So like the recursive memoized one is the most amount of space. What's up?
Wouldn't it still be linear though? Because of the memo will grow, will have as many elements as n minus 1 roughly.
Yep, that's right.
And the stuff on the call stack is still the n.
That's right.
So it will be like, will it be like 2n and then just n?
Exactly.
Okay. Cool.
Yeah, so they're both n. But generally with space, we don't use big O, but it's not wrong to use big O. It's just when people say big O, they're talking about time. Just because like upper bound stuff doesn't matter as much with space. But no, you're not wrong. They're both order of n space. Just one is twice as big as the other.
Cool, thank you. So this is pretty much it. Another problem that I wanted to get into, but did not feel comfortable with just yet, was the problem that Ben mentioned, which is the coin change problem. And that problem, I found a video that I'll share that the guy explained the approach. He actually didn't write any code, but from that video, I was able to code the bottom-up approach. And I wanted to do the top-down, which using memoization. But I didn't, I couldn't figure that one out. But I want to pass the problem along, and I want you to, you know, try it on your own, see, watch the video. And even before that one, there is this problem that's all dynamic programming as well.
It's easy. That sounds crazy.
Yeah,
probably
lead
not
code.
programming is easy.
Lead code. Yeah.
I mean, the one that we were doing, the coin one we were doing was medium, and it was hard. It was a really tough one. We came up with some really good solutions, I think, but they weren't optimal. Like, they weren't correct. They were just like pretty good last week.
So this is one. Cracking the Coding Interviews has a different version of this. The Cracking the Coding Interview is a child running a staircase, and they can hop on either 1, 2, or 3 steps. So it's a bit more than this one. This one has 2 steps. And a cool thing is here, some lead code problems have the solutions here. So if you get stuck, this is a good read. Sometimes they even have a visualization, similar to what we saw, and so on. Oh, this one even have a video. That's cool. So yeah, don't feel discouraged to look at the solution and study the solution. For problems like Fibonacci, for instance, or even this problem, I think this one we can start to sort of discern after we have explored a little bit of dynamic programming. We know that it's probably gonna use some memoization and stuff like that. The other problem is the coin change problem. And I like this visualization they have here. So yeah, you're giving coins of different denominations and a total amount of money. You have to write a function to compute the fewest number of coins that you need to make up that amount. If the amount of money cannot be made up by the combination of the coins, just return -1. So let's say you have coins. Some of you have already saw this. Let's say you have coins of like 1. Let's say like 1 cent, 2 cents, 5 cents. Even though, well, that's not American currency, Colombian currency. And basically, we have to see if we can make up 11 from this. The output here is 3 because you can take 2 coins of 5 and 1 coin of 1, and that will give you 11. And so on. What I wanted to show you here is just this graph that I saw around here. So actually, I think I have it open here. This one.
I think that this is a quintessential dynamic programming in the way that dynamic programming was taught to me, which maybe this tree is explaining us, which is like, what is the best answer for like, so this is like for 2 cents, for 3 cents, for 4 cents, for 5 cents, for 6, etc. And then, I sort of tried explaining this last time, and it's like the algorithm, the way that you think about it is like, okay, the best answer for 1 cent is just 1 penny. Awesome. Best answer for 2 is just one of the 2 centers. Great. Best answer for 3 is just one of the 2s, one of the 1s. Easy, right? But then once you start getting to the hard ones, the way you think about it is you say, okay, I'm trying to solve K, right? Some number K. Let's say it's like 1,000. And if you assume that you've solved all the previous ones, I've solved 1, 2, 3, 4, 5, all the way up to K minus 1. Then I can say, all right, what's the best answer for K minus 1? Because whatever the best answer for K minus 1 is, then I can just add 1 penny to it, and that would be the best answer for K, right? But maybe actually there's like, let's say it takes 100 coins to get to K minus 1, but it might take only 75 coins to get to K minus 5. And since I have a 5 cent coin, then I could get to where I am at 76 coins, which is better because it's, 75 coins to get to K minus 5, and then 1 5-cent coin to get to K. And so what you do is you're at K, and you basically look backwards based on how big of your coins are. You look backwards for your 1 center, 2, 5, 10, 15, 25, however big your coins are, you look back. M, let's say K times, where K is the number of coins, or C times, C is the number of coins. And of all of those solutions, whichever one is the smallest, your answer is that one plus 1. Does that make sense? And that's that's like the quintessential dynamic programming. It's like super, like the pièce de résistance.
Questions or thoughts? So yeah, basically this is actually I wanted like at least give a glimpse of this, but basically we have coins 1, 2, and 3, and we have to make a change for 6. So I was trying this earlier, and I was looking at something like this basically. Let me move here. These are the ways that I thought we could make a change for 6, just sort of by hand doing it basically. So like 6 coins of 1, 4 coins of 1 and 1 coin of 2, 3 coins of 1 and 1 coin of 3, 2 coins of 1 and 2 coins of 2, and so on and so forth. And then I plot out like how many coins that will be. So the first one is 6 coins. The sixth one is 5 coins because it's 4 coins of 1 and 1 coin of 2, and so on and so forth. And then I saw like, well, 3 will be the lowest we can go, basically, which will be actually not the lowest we can go. The lowest we can go in this example is if you use 2 coins of 3 of the denomination of 3, basically. And the way something that I realized was that I was doing it sort of like this particular order, but the algorithm will actually try different combinations of this in the sense that it might try with a 3 first and then 1, 1, 1, 1, 1. And that's what I wanted us to like just scratch here at this graph basically. So the algorithm will with 6, what it will do is it will subtract each coin from it. So we can see it's wide enough. With 6, it will subtract 3. Meaning like I use a 3 coin, and it will try something with that. It will try to use the second coin of 2 and subtract it from 6 and do something with that. And same for 1. And the tree will go depth first on the left side. So we'll see that this one goes first. In fact, so here, once this is the recursion tree, and once you have this, basically is what is the smallest or the shortest branch, basically. This is another sort of way of thinking about it. The shortest branch is this one here on the right, where we use 1 coin of 3, then that gives us 6 minus 3, 3, and then we try to do the change. Can we make change for a coin of 3 with what we have with coins 1, 2, and 3, and we just repeat the step. We subtract 1 from 3 and do that. We subtract 2 from 3 and do that. Subtract 3 from 3 and do that. And we can see here that the shortest branch is this one on the right, where we use exactly 2 coins of 3. But the idea here is that the algorithm is trying sort of every single possibility at every single step. And on top of that, the idea of memoization, the space for memoization here is, for instance, we could take a look at, let's say, F2. We calculate F2 in a bunch of different places. F2 here, F2 here, F2 here. We can memoize that as well. And
yeah, this is like a different way of visualizing what I was saying, right? Because you're working backwards, right? You're saying, I want to find 6. Well, let's minus 3. Let's find the best answer for 3. Well, the best answer for 3 is F3. They draw it in a few different places, right? I see 3 F3s.
Here,
right?
Here.
But like generally the way you actually implement these is not through a recursive tree like this. In fact, what you do is you do bottom up.
That's correct. I think maybe we can take a look at that one next time. I think this is a. I remember when I finished Pursuit. One of my friends, I think he works at Spotify now. He got this question in the Spotify interview. This exact same one.
Wow, really?
And he actually he was good. Like he knew how to make this one. And I remember him explaining this problem to me. And I remember he drawing something similar to this, but I did not get it. And that, what I want to say with that is that this is hard. You need to look at it a few times. This is my second time looking at this, and I think I have a better understanding of how it works now. And I implemented the bottom up approach for this one. I want to implement the top down recursive one. But yeah, just the lesson there is sometimes it takes more than one pass through. Actually, most of the times. Okay, so hopefully that was a glimpse at it. Yeah, I'm gonna put some resources in the online resources channel for this. As Ben said, like this is probably you're never gonna see it at your daily job. Like you have to do something using dynamic programming. Unfortunately, we might get one of these in an interview, and we have to prepare for that. At least let's be aware of that. Cool. Any final questions or thoughts before we cut it short here? Okay. My suggestion will be try the. Oh, I think maybe I saw a question behind. Maybe. No.
Yeah, I just wanted to say it's a lot to process.
Definitely. I no, I 100% agree. I think it will be if there's still parts of the Fibonacci one that doesn't feel like super clear, experimenting playing with it more. Reading and maybe even watching some visualizations as well. I'm sure YouTube has a few as well. Again, as on one go, we very rarely get. But I appreciate that honesty. Anything else? Anybody else? So my recommendation will be definitely like look into if you have the Cracking the Code interview book. The Cracking the Code interview book goes in depth into this that we saw today, and especially with the Fibonacci example. And it has some good other problems that are similar, like the climbing the stairs. I think that will be the next one. It's actually the next one that the Cracking the Code interview has, and maybe we can start. You can start thinking about this with what we have today. Okay, so that is it for today. Ben, anything you want to add or say?
No.
Cool. All right, everyone. I hope you have a good night. Glad that you came and got some exposure to this. I hope everyone has a good weekend. Our weekend. We'll see you all on Saturday.
No, y'all.
Thank you. Good night all.
Good night.
Good night.
Bye. Good night.